This is 6.2 Systems of Linear Equations in Two Variables. A system of two linear equations in two variables has the following form. Both variable terms are linear, meaning the exponent is a 1, and then we have those added together, or you might have subtraction in here, equal to a constant. And then you have two more terms for another equation being added or subtracted equal to a term. Sometimes they might be written such as 3x minus 8y equals 12 and y equals 3x plus 2. This is still a system of linear equations in two variables, just not written in standard form. To solve a system of linear equations algebraically, we can use substitution or elimination method. Um, in the case of the both equations being the standard form, elimination would definitely be the easiest. If the two equations are set up like this, substitution might be the easiest. But generally speaking, elimination method is easier. In 6.2, we're going to look at the solutions of a system. The number of solutions in a linear system in two variables is going to be one of three types of solutions. Exactly one point, or one solution, which would be the intersection point of two lines. We might have no solution where the system is inconsistent if the two lines are parallel to each other. And finally, we could have infinitely many solutions, which is a dependent system, if the two lines end up being the same. Okay? So if they intersect, if you graph the two equations and they intersect, that is one solution. If they are parallel, that would be no solutions. If they overlap, that would be infinitely many solutions. And when we have infinitely many solutions, what we are going to do, let's say we find out that we have, well, let me back up here a second. When we have one solution, we're going to find out, once we go through this work to do solve the system, we will find an x equals a number and a y equals a number, and we'll come up with an ordered pair such as AB, where A and B are real numbers. To find out if a system is no solution, what will happen is, let's say we have 3x plus 2y equals 8. And we have negative 3x minus 2y equals 2. Okay? Let's say we've done the work to get these to a point where we can add these together using the elimination method to eliminate a variable. And we end up getting 0 here. We end up getting 0 here. And we end up getting some kind of number over here. Anytime you end up with different numbers equal to each other, that is going to be no solution. If we do the work to use elimination method, and we end up with two equations that will give me 0, 0, and 0, where I have two exactly same numbers. If you use elimination method, you'll get 0 equals 0. But if you use substitution, you could get any number equal to itself. And if we get that, if we get infinitely many solutions, what we're going to be doing is taking, let's take this for equation for example, and we're going to solve it for y. We're going to take 3x plus 2y equals 8. we will subtract the 3x. 2y equals negative 3x plus 8. Divide by the 2 and get y equals negative 3 halves x plus 4. And what we're going to do with that is we're going to write an ordered pair in using variable expressions. So if we just use x as itself, then y would be negative 3x plus 4, negative 3 halves x plus 4, because y is equal to that. So instead of writing x and y, because that doesn't do much for us, we're going to write our ordered pair in terms of x. So we're going to put negative 3 halves x plus 4, and here is our ordered pair. That's supposed to be a 4, okay? And that's a way to write a solution representing infinitely many solutions. And I could, if I need to find a specific point anywhere in the system, I can plug in for x and find out what my y is. Okay? Let's look at a linear system that has one solution. If we take this equation here, we're going to follow the same 3 steps that we covered in section 6.1. And we're going to look to add these together and eliminate a variable. Right now, if I look at these variables, I could multiply x by the 3 up here and get 3x and negative 3x. Or I could multiply either one of the equations by negative 1 to end up with a positive y and a negative y. So I'm going to go ahead and do that. I'm going to multiply the first equation by negative 1, and that will give me negative x minus y equals negative 6, and negative 3x plus y equals 2. When I add these together, I will get negative 4x 0 and negative 4. When I divide by negative 4, I will get x equals 1. So I've done step 1 and step 2. Now I'm ready for step 3. And I'm going to plug that into either one of these two equations. Let's go with the first one. I get 1 plus y equals 6. Subtract the 1, and I get y equals 5. And my solution will be 1, 5. Okay? And if I plug that back in, the first equation, 1 plus 5 equals 6, and negative 3 times 1 plus 5, we're going to see if that equals 2. Um, and I show that down here. Negative 3 plus 1 plus times 1 is negative 3, plus 5 is 2, and that does work. If I have to graph this, I would go ahead and put them into slope-intercept form. So I would get y equals negative x plus 6 and y equals 3x plus 2. And I would graph my y-intercepts and use my slope to create the graphs. So let's go with this first one. If I go with my intercept of 6, negative 1 would be down 1 to the right 1, down 1 to the right 1. So I'm going down to the right, down to the right, down to the right, down to the right, okay? And I could plot these points and graph my line. With my 2, I'm going up 3 units, 1, 2, 3, and to the right 2 units, and I plot another point, and I can see how I overlapping my points as I'm plotting them, and I could draw my line, and my intersection point would be right there at 1, 5. Oh, up 3 and over 1, not up 3 over 2. Okay? let's look at a linear system that has no solution and see what happens there. Now I know on that last problem in the actual notes I gave you in class, I multiplied the first equation by 3, but that just goes to show it doesn't matter which method you use or which one you multiply, you're still going to end up with the same answer. Okay, let's look at number the second example. Okay, here, if I look at this, I see here I can multiply the x by -2. Let's go ahead and do that. -2x plus 2y equals -16. And -2x plus 2y equals 1. When I set this up and I go to add, I'm going to get, oops, I'm sorry. This should be positive 2x. I'm not multiplying by -2, I'm multiplying by positive 2, which means I will get 2x minus 2y equals 12, not 16. Okay, so now when I go to add, I get 0. Here I get 0. And here I get 13. Okay, since 0 does not equal 13, there's nothing we can do here. This is no solutions. For this next example, it's going to show us what happens when we have infinitely many solutions. Okay, when I look at these two first terms, I can multiply x by 5 and get 10. So I'm going to multiply by 5. In the notes it says -5, but really should be have the opposite. So I'm going to get 10x plus 25y equals -5. Oops, I don't need to draw that line. Y equals -5. Okay, 25. Let's turn it. -25, right? No, it is -5. What am I doing? Okay. And then the second equation is -10x minus 25y equals 5. When I set this up and add, I get 0, 0, and 0, and 0 equals 0. So that is infinitely many solutions, IMS, okay? And just like I stated before, if I take one of the two equations um, and solve for y, let's take this first one here, 2x plus 5y equals -1. I'm going to subtract the 2x. All right, let me see, I might have it down here. Okay, so I'm going to write one of the equations in slope-intercept form. Here I'm taking -25y, let's see, -10x minus 25y equals 5. I'm going to add the 10x to both sides, and that gives me -25y equals 10x plus 5. I'm going to divide by -25, and I have to divide each term, and I end up with y equals -2/5 minus 1/5, 2/5 x. And sometimes the book likes to put in x equals t. You can do that, or you could just leave it as x. Okay, and if I just leave it as x, and my y value is the expression over here, so -2/5 x minus 1/5. But if I plug in t for x, then all I'm doing is changing these two variables. So t and -2/5 t minus 1/5. So in the book, if you ever see that with the t, that's what they're doing, is they're just replacing x with t. Okay, and so the ordered pair is now that. Okay, and that's it for section 6.2.